You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Professor Avi Loeb. Avi Loeb is the Frank B. Bird Junior Professor of Science at Harvard University, Chair of Harvard's Department of Astronomy, Founding Director of Harvard's Black Hole Initiative, and Director of the Institute for Theory and Computation within the Harvard-Smithsonian Center for Astrophysics. He also chairs the Advisory Committee for the Breakthrough Starshot Initiative, serves as the Science Theory Director for all initiatives of the Breakthrough Prize Foundation, as well as Chair of the Board on Physics and Astronomy of the National Academies. He is the author of 4 books and over 700 scientific papers. He is an elected Fellow of the American Academy of Arts and Sciences, the American Physical Society, and the International Academy of Astronautics. In 2012, Time selected Loeb as one of the 25 most influential people in space.
Dr. Avi Loeb, welcome back to the program.
Thanks for having me.
Now, Doctor, you worked extensively in black holes and the theories regarding them. And now we actually have a picture of sorts of Sagittarius A star. What's your reaction to that? What did you think upon seeing the image of the central supermassive black hole of the Milky Way?
Well, in fact, 2 decades ago, I worked on the expected image that we might get. And in fact, I brought to the Center for Astrophysics at Harvard the person who founded the Event Horizon telescope. So we started the work from there. And I was involved in the early stages of the project, promoting it and making theoretical predictions for what they might find. And we actually wrote a paper with my postdoctoral fellow, Avi Loeb, arguing that it's not the black hole at the center of the Milky Way that the only one that we should look at. There is another one in the galaxy M87. And we wrote the first paper talking about it and forecasting the image of that black hole. And it ended up being the first one, of which an image was publicized. M87 is a galaxy that is about 2,000 times farther than the black hole at the center of the Milky Way galaxy. But the black hole there is 1,500 times bigger in mass. So you end up with an image of the silhouette which has roughly the same angle on the sky, and you can detect both of them. And so I'm really pleased to see those images, the face of the black hole in the middle of the Milky Way galaxy. And now that we have that image, it can be a tourist destination. And you might ask, why would the tourists go there? Well, if you go to the location, for example, of the photon ring, it's really an amazing place, because you can look forward and see your back, because light makes a full circle around the black hole. Also, if you get close to the horizon of the black hole, time is ticking more slowly there, so you can outlive your friends on Earth in a sense, because time is progressing more slowly there. And also, I can imagine that we can give discounted tickets to string theorists to go there, because if they get close to the singularity of the black hole, they can test their ideas. And of course, these will be one-way tickets.
Do you think that black holes, because of that reason, that alien scientists could go there and start testing string theory and things like that, do you think that we're barking up the wrong tree perhaps by looking for technosignatures when we should really be looking at black holes for any evidence of alien civilizations, because that's where they would locate their physics labs, perhaps?
No, I mean, if you think about about it in practical terms, the only benefit of being close to a black hole is that you can throw your trash to the black hole and get clean energy in return. And the efficiency of converting trash into clean energy is the highest that you can imagine, because about 10% of the rest mass can be converted to radiation in the vicinity of a black hole. So that's a practical way of getting a lot for what you deposit there. And so other than that, it's actually quite a risky environment, because objects move very fast near a black hole, and that can create a lot of friction and damage to anything that you possess. And moreover, very often these environments light up. The matter that is falling into the black hole shines very brightly because it heats up, and so it's a risky environment. In fact, we wrote a scientific paper saying that if the black hole at the center of the Milky Way, Sagittarius A star, were to be fed, right now it's starving, and that's why we can look through the galaxy and get very close to imaging the shadow of the black hole. But if it were fed, I mean, it's actually underfed by almost 1 billion times than what it can be fed with. And if it was fed 1 billion times more, then all the habitable planets out to a distance of a few thousand light years from it could have been sterilized. There is ultraviolet radiation, there are X-rays emitted by such a black hole when it accretes a lot of gas, and therefore it, life is not easy close to it. And so I would actually caution civilizations from getting too close to a black hole. The sun is located 24,000 light years away from the center of the Milky Way, and that's a relatively safe environment. And it might not be by chance. If we were much closer, then episodes of the black hole at the center lighting up could have sterilized the Earth.
Now, people have brought that up before, then said that the orientation of Sagittarius A star might actually be pointed at us. The relativistic jet might be pointed at us. Does this new image clear that up? I mean, what is the orientation of it towards us? And if it started accreting a bunch of matter, could that be a problem if the relativistic jet is pointed towards us?
Yeah, so first of all, we don't know that this black hole produces jets. Usually jets are produced by black holes that are spinning. And so there are two questions here: whether the black hole is spinning, and the second is whether the orientation of the pole, the direction of the spin, is towards us, because that's usually the direction of the jet. And the Event Horizon Telescope team produced a lot of computer models trying to simulate the image that was observed, and they claim that among the many models that they looked at, the ones that appeared most consistent with the data correspond to a nearly face-on situation where, if there is a jet, we are in its direction, so to speak, and also to a situation where the black hole is spinning. And I think this conclusion may not be right, because, for one thing, the chance of the black hole to be pointing at us, the jet pointing at us, is really small. And because that would mean that it's, perpendicular to the direction of the disk of the Milky Way. So if you imagine material from the disk of the Milky Way falling into the black hole, then the black hole should be spinning in the plane of the Milky Way galaxy. But what you need here is that since we are in the plane, you need it to be spinning exactly perpendicular to that, which seems really strange. And the other thing is, we analyzed with a postdoctoral fellow, Giacomo Fragione, we analyzed the orbits of the stars in the vicinity of the black hole. And they seem to lie in two preferred planes, the stars near the black hole. And just like the planets moving around the sun, there seem to be two planes from where they they orbit, and we showed that if the black hole was spinning, then Einstein's theory of general relativity would have basically blurred those planes. You wouldn't see two distinct planes, because on a relatively short time scale, the stars would shift away from the original birth plane that they were at. So we were able to argue that the spin of the black hole must be small. And that is opposite to the inference from the Event Horizon Telescope image. And so my guess, and mark my words, is that something in the models that they were considering or using did not include all the physics. They didn't have all the ingredients that they should have had to produce proper images of the black hole. And obviously, to generate the image, you need to assume something about how matter is falling into the black hole, how it moves around it, how you produce the radiation. There are a lot of uncertainties on these issues, and they must have assumed or explored a certain range of parameters, but my guess is they are missing something, and that's why they reached those conclusions, which do not seem to be very likely to me.
Now, the formation of a non-rotating black hole. So of course, you have a star collapsing in on itself in standard black hole formation, that if that star's rotating, it's going to rotate faster and faster as it collapses. So how do you create a non-rotating black hole?
Oh, yeah. So first thing to keep in mind is this black hole at the center of the Milky Way is 4 million times the mass of the sun. Okay, so it's 4 million. It weighs as much as 4 million suns. So it was not the result of the collapse of a massive star, but it was a result of infall of gas into a seed black hole, or the mergers of many black holes. Now, if you imagine mergers or even accretion of gas, through episodes. So at some point in time, there is a cloud of gas falling into the center, and it's orbiting in some plane, some preferred direction. It will give the black hole spin according to the direction that it's orbiting in. And then if there is another cloud of gas coming in a different direction, it will give a different spin orientation. And so you keep adding these episodes, and they add up. If they add up randomly, you will end up with no spin. And in the same way, if you were to merge black holes, suppose each black hole has some spin, but they arrive to the merger point, at random, then you would average out the spins of all the building blocks that you put together to make the final black hole. So it will average out to zero. So one simple way of getting very low spin is if you were to start with building blocks, each of which were randomly oriented, and then you put them together and they cancel out. So you end up with a very small spin. On the other hand, the way to build a very high spin is if instead of having many building blocks, for example, you have one major episode of growth for the black hole, and you always maintain the same orientation of the matter that falls into the black hole. So you keep adding rotation in the same direction, and then you get a final black hole that is spinning very fast. So it all depends on the history of how this black hole came to exist. And in the context of galaxies like the Milky Way, you would think that there were many episodes of small building blocks coming together, and that's why a very low spin is quite likely.
Is there any effect, and I would imagine there's not, but you would know and I would not, is there any effect on a spinning black hole and the behavior of its event horizon? In other words, if you imagine a star that's spinning very rapidly, it will sort of crush, and elongate. Can that happen to a black hole, or does just the laws of gravity prevent it from being anything except an identical event horizon to a non-spinning black hole?
Oh, no. We know the solution to Einstein's equations of general relativity in the case of a black hole with any arbitrary spin. And this is called the Kerr solution, after a physicist with the last name Kerr that lived in New Zealand. And And that allows for any arbitrary spin. And now, of course, the event horizon, the location of and the shape of the event horizon depends on the spin. So just to give you the two extremes, when you have a non-spinning black hole, zero spin, that is the solution that Carl Schwarzschild derived back in 1915, a few months after Albert Einstein came with the equations. Einstein published his equations in November 1915, and then a few months later, he couldn't get an analytic solution to the full equations. And Karl Schwarzschild, he basically volunteered to serve in the German military. He was the director of the observatory at Potsdam at the time, and about 40 years old, and felt very loyal to the German nation, and volunteered to the military and went to the German front, and then derived a solution while being there to Einstein's equation, and sent Einstein a postcard with a solution. Einstein was thrilled to receive it and publicized this solution. And then a few months later, Karl Schwarzschild died at the front from some rare lung disease. Just to illustrate the fact that if you want to derive the consequences of a theory, you better be a pacifist than being a patriot, because then you have more time to work out the solutions. So at any event, Einstein was a pacifist, Schwarzschild was a patriot, and therefore Einstein had more time to derive consequences of his theory later on. But at any event, the Schwarzschild solution is the solution of a black hole, a point mass, and that's for a non-spinning black hole that has no spin, and the solution is really simple. There is an event horizon at a distance that is twice times Newton's constant times the mass of the black hole divided by the speed of light squared. Okay, and that's called the Schwarzschild horizon. And it's spherical. It's a spherical shell around the point mass. In the middle of it, there is a singularity where Einstein's theory breaks down. We don't know what happens. You need to incorporate quantum mechanics to figure out what happens near the singularity, because the curvature of space and time diverges there. So clearly, Einstein's theory doesn't have quantum mechanics. That's why it breaks down at the singularity. And we still don't have that unification of quantum mechanics and gravity, so we are still faced with that problem. But at any event, about more than half a century later, Kerr derived the solution for a spinning black hole, and that's quite different in the case where the black hole is spinning fastest, near the speed of light. In that case, the horizon shrinks by a factor of 2, so it becomes half in the equatorial plane, half the Schwarzschild radius, and then it's squashed. The horizon is not spherical anymore, and there are lots of interesting phenomena there that we don't have time to get into in the Kerr case. But in principle, you can extract energy from a spinning black hole by having matter near it, or matter with a magnetic field. It's sort of like a flywheel that you can tap to and extract energy from the spin of the black hole. And we believe that the jets that we see in distant galaxies that move near the speed of light are being powered by the extraction of energy from this flywheel of a spinning black hole.
Now, one question about Kerr. Now, in his ideas, there is the concept of the Kerr ring in a spinning black hole, and where you don't have a point, you have a ring. And my question is, now some people have advanced the concept of maybe this is a wormhole, maybe this leads somewhere. Do you think that has legs, or do you think it's just simply a dead end? You don't go anywhere, you just add your mass to the black hole, as opposed to actually going anywhere, if you could get through it with some sort of exotic matter or whatever that people have pointed out. But do you think that it is a solution, possibly, that it's a rip in space-time that happens in the center of the black hole? Okay,
so first, Roy Kerr derived his solution a year after I was born, 1963. It's 59 years ago, almost 60 years ago. Before that, Einstein, together with Nathan Rosen, were wondering, for the Schwarzschild solution, what lies inside, and if matter falls into it, what happens to it? Can it go somewhere else? And they came up with a paper that suggested some bridge that you can sort of imagine two Schwarzschild solutions, where if matter getting into one of them comes out from the other side, or and then that led to additional work on wormholes. Now, the situation right now is without quantum mechanics, these wormholes cannot exist, because they basically snap on a time scale that is too short for anyone to go through them, for any matter to go through them. So Einstein's theory of gravity doesn't really allow it. But then if you imagine quantum mechanics being incorporated in a way that, you make the wormhole from matter that is quite unusual, matter that has negative pressure, which we, don't have access to. We cannot engineer such substance. But nevertheless, if you imagine substance with negative pressure, and I should say, we do know that the universe has such substance. It's called dark energy, which causes the accelerated expansion of the universe, but that's considered to be the energy of the vacuum, and we don't know how to manipulate it to make a wormhole, for example. But if you imagine that you can do that, the question is, can we imagine solutions that involve wormholes made out of material that has negative pressure? And people have tried to derive such solutions. There are claims recently that they can have such stable entities like wormholes that you can go through. But I would say all of these are tentative claims. First, for the reason that we don't have in our possession the ability to engineer such matter with negative pressure, and second, because even the mathematics is not yet on a solid footing. So right now, I would probably bet that wormholes do not exist in nature, that we can't make such things. But let's see. I mean, physics is only a century. The modern physics is only a century old. We still don't have a unified theory that marries quantum mechanics with gravity. So there might be surprises in the future.
Now, about surprises and about the current state of where we're at, do you think within our reasonable lifetime we will see a unified theory that bridges the gap between quantum mechanics and general relativity?
So here is what I learned in the about 4 decades that I practiced physics. I learned that the only way for us to make real progress in our understanding of nature is by being guided by evidence, by experiments. And the same should apply to how to unify quantum mechanics and gravity. I mean, the thing is that very brave theorists, like 4 decades ago, thought that they can just do it by pure thought. And so the most popular theory right now is string theory, but they thought that it would lead them along a path such that they would be able to get a single solution. And turns out there are many possibilities. And that's exactly why we need experiments, we need evidence to guide us. Nobody would have thought about quantum mechanics a century ago unless experiments told us that indeed it exists. And Einstein actually had difficulties interpreting quantum mechanics. He was resisting the simple interpretation of those experiments, and he was wrong. He thought that the entanglement is not real, and now we use it in devices, quantum computers and so forth. So, I mean, it was clearly not intuitive to him, and nobody would have come with quantum mechanics out of pure thought. Okay, and just to think that we can figure out nature without doing experiments, I think is very arrogant. So the only way by which we can make progress is through experiments, through collecting evidence. Nature is much more imaginative than we are. So my point is, we tried to follow the path of string theory just based on pure thought for by now 4 decades. We haven't yet come up with any predictions that can be tested experimentally. And what are the avenues for us to make progress? Well, there are two places in the universe where quantum gravity is needed. One is near the Big Bang. What happened close to the beginning of the universe. Back then, the conditions were such that both quantum mechanics and gravity were important. And the second is the singularities of black holes. Okay, so by getting more data on black holes, we may get closer to seeing things that guide us. We can also get closer to the Big Bang by peering back in time, detecting, for example, gravitational waves from that time or other signatures. These are the best hopes for us to be guided. And I would basically say, let's wait until we get to the point where we get some experimental evidence about perhaps the singularity of the Big Bang or the singularities of black holes. And before we get there, before we have something to guide us, we might be going in the wrong directions.
Now, some people have pointed out that the universe and the Big Bang somewhat resembles a black hole in certain ways. Do you think this is superficial, or do you think that's actually a helpful direction to go in to look at whether or not we live in the interior of a black hole?
Yeah, so the Big Bang was a singularity, and indeed in black holes you do have a singularity, but they are of a different type. The Big Bang singularity was a singularity in time. There was a point in time, we know the universe is expanding. If we go back in time, there was a point in time where the density of matter and radiation were infinite. You just, as the universe expands, it gets rarefied, but if you go back in time, there was a point where everything diverges, and that's called the Big Bang. And that was a singularity in time. It was not in space, because the universe started pretty much uniform, very close to being uniform. We know that by looking at the cosmic microwave background. We know that the conditions, for example, 400,000 years after the Big Bang, the conditions were uniform throughout the universe to 1 part in 100,000. That's a very we measured it. We measured the small changes between one location in the universe and another at that early time by observing the cosmic microwave background, and the differences were tiny, 1 part in 100,000. So the universe started uniform in space to 1 part in 100,000, but it had a singularity in time. When you consider a black hole, it's exactly the opposite. In fact, the Schwarzschild solution is a solution for a stationary object, an object that doesn't evolve in time. It's the same at all times, but it has a singularity in space, so to speak, in the sense that inside the event horizon there is a point where everything, the curvature diverges, and that's probably where all the matter goes when it falls into a black hole. I had once a flood in the basement at my home, and I called the plumber. We went down and we found that there were tree roots blocking the sewer, and we cleared the tree roots. And then it led me, in those hours when we were working on that, it led me to think about what happens to the matter that goes into a black hole. Because until then, I was just taking it for granted that all the water in my home is going down the drain, and I don't care where it goes. But once this sewer got clogged, it reminded me that there is a place that collects the water. And so I thought, okay, matter falls into a black hole. Where does it go? Now, you can imagine two things. You can imagine, just like the sewer case, that it goes through the black hole into some other space-time, some other universe or something. Another possibility is that, this sewer is clogged. Okay, so there is an object that collects the matter on it. And this object could have the maximum density that we can imagine. For example, it's called the Planck density, where, that's the maximum density that you can achieve for matter. And you can just imagine this object collecting all the matter that falls onto it at the Planck density and being there at the center. We can't see it because it's hidden behind the event horizon. And we don't know what the answer is, and unless if we go on a journey into a black hole, we would figure it out, but it would be too late because we would crash on this object. We wouldn't be able to communicate it back to the rest of the world, But it's a very interesting question, and it's unsolved at the moment. We don't know what the right answer is. And one way to figure it out is if we had a theory of quantum gravity, it would make a prediction about what happens to the matter as it falls into a black hole.
Now, that might be an interesting tangent to go on. The environment of a black hole, were you falling into it? Now, I would imagine that your first problem as you fell into the black hole would be the accretion disk and the immense heat and X-rays, everything that's coming off of that. But then spaghettification. So even if, and we're barring exotic matter here, but even if you were simply falling into the black hole, you probably wouldn't even make it to the event horizon.
Oh no, so an astronaut would make it. A star like the sun would not make it in the case of Sagittarius A star, the black hole at the middle of the galaxy. But in M87, just to give you an example, in the case of M87, even a star will get swallowed whole once it enters to the event. It will not get spaghettified. And the reason is that the bigger the more massive the black hole is, the less curvature of space and time there is at the horizon. So it's really the tidal effect, the same effect that the moon exerts on the oceans. That's called tides. So the moon is closer to one side of the Earth, and it pulls on the water on the surface of Earth, and makes and makes a bulge, and that's the tide that we see in the ocean. Okay, on the side closer to the moon. It's just the difference in the gravitational force that the moon exerts on the two sides of the Earth. On one side, the force is stronger, and that's why the water comes, more to that side. So that's called the tide. And if you imagine an object like a black hole and a star like the sun getting close to it, then the black hole will exert a tide on the star. So it will act more strongly on the side closer to the black hole, gravitationally. And if the difference in forces between the two sides of the star, if that difference is bigger than the force that binds the star, the gravitational force that the star is bound by, then the star will get ripped apart and get spaghettified, as you were alluding to. That's called the tidal disruption of a star. And for black holes like the one in the middle of the Milky Way, Sagittarius A star, indeed, a star getting within 10 times the Schwarzschild radius of the star, of the black hole, the star would get spaghettified, a star like the sun. And we calculate that roughly every 100,000 years, such a thing happens, because stars get scattered to the vicinity of the black hole, and you get a flare that results from the disruption of the star. But a human, an astronaut, is much smaller than a star like the sun, and it's not held by the force of gravity, it's held by chemistry. So if an astronaut gets close to the horizon of Sagittarius A star, nothing will happen to the astronaut, because the size of the body of the astronaut is only a couple of meters. The sun is much bigger. So the difference between the toes and the head of the astronaut, the difference in forces, is not big enough to rip the astronaut apart, except when the astronaut falls into the horizon. Eventually it gets close to the singularity, where the force is big enough and the astronaut will be ripped apart. By the way, I once explained that to students in the class of in the kindergarten of my daughter. Invited me to speak in front of the class, and I explained this. And then the teacher stopped me in the middle of the story and said, "Please stop. The kids would have nightmares if you continue." So they were fascinated by this question of what happens to an astronaut. Now, the one thing I wanted to mention is, if you make the black hole even bigger than Sagittarius A star, then if you make it like bigger than 100 million times the mass of the sun instead of 4 million the mass of Sagittarius A star, then even a star like the sun will not get ripped apart, because the black hole is so big that there is not much curvature in its vicinity near the horizon. So So a black hole like M87, if a star comes close to it, it doesn't get ripped apart. It can go through the horizon. Eventually, when it gets close to the singularity, it will get ripped apart, but we won't see that because it's hidden behind the horizon. So tidal disruption events of stars happen only, for relatively small black holes. And I should say there is another risk of being near a black hole, that two stars can collide with each other. This is a process that I wrote a paper with my student on just last year. And those collisions can be very powerful because stars are moving close to the speed of light near a black hole. So imagine, two stars like the sun that happen to collide with each other. They would release a huge amount of energy. You would have an explosion if they were to collide near a black hole.
Colliding stars. All right. Now this has got to be one of the few ways this can happen, because if you have a merger, like the coming merger with the Andromeda Galaxy, it's unlikely that stars will hit each other, but in a black hole environment they can. Is this something that could create something like a gamma ray burst, or one of the unexplained, fast radio bursts or something like that? It's just mysterious signals that we see in nature. Could this be a possible starting point for that?
Yeah, well, it could be. With respect to gamma ray bursts, we think that there are two classes of processes that lead to gamma ray bursts. One is when you have a star collapsing, the core of a massive star collapsing to make a black hole. This is a stellar mass black hole that weighs somewhere between a few times the mass of the sun up to 100 times the mass of the sun. In that case, the black hole can produce a jet if it's spinning, and the jet will drill a hole through the envelope of the star, and you would see it as a gamma ray burst. So that's one. And we know that this happens because we see that in the case of long duration gamma ray bursts that last many seconds, that in fact very often they're followed by an exploding star. And one way to understand it, we see the afterglow, we see a supernova that takes off afterwards, but basically when the jet drills a cavity through the stellar envelope, it also releases energy and pushes the envelope to make the star explode. So that is one type of gamma ray burst sources. And the second type is when you have two neutron stars. A neutron star is the core of a massive star that ends up collapsing but doesn't make a black hole. It makes a star that with a density similar to the atomic nucleus, but the size of a city like Boston, 10 kilometers in size. And such a star, the mass of the sun, a size of a city, is very compact and dense, and it's called a neutron star. And we know that supernova explosions very often lead to the formation of a neutron star. We actually saw evidence for that in the case of one nearby supernova in 1987 that led to the production of neutrinos, which indicate the formation of a neutron star. So anyway, when two neutron stars are in a binary system, in a pair, and they collide, then you can get a gamma ray burst in a jet that is generated out of that collision. And another interesting aspect of that collision of two neutron stars is that you eject some material rich in neutrons out of this collision. And turns out that this is probably the most prolific source of the heavy elements that are called R process, elements like gold or uranium, the sources of all evil on Earth. Gold. If we were just close to a neutron star merger event, we would have a huge amount of gold available to us on Earth. It's just that, these collisions are so rare that gold is precious because on average there is not much gold. But if the Earth was would have been born close to a site where two neutron stars collided, then we would have plenty of gold everywhere. And uranium in much the same way, So if you imagine civilizations that happen to be born close to a neutron star merger event, they would have a lot of gold and potentially a lot of nuclear weapons.
Just what we need, a universe full of nuclear weapons. Now, my last question for you is to get weird in regards to the environment of a black hole. Now, a star is not the only thing that can fall into a black hole. You could have a neutron star, very high density object, or you could have two stars colliding. And correct me if I'm wrong, I think this is the Chandrasekhar limit, where you actually have something collapse into a black hole right next to the black hole because two stars collided. Can that occur? I mean, and can we detect it?
Oh yeah, definitely. So what we most easily detect is radiation, light, and any such event of the type that you mentioned it results in an explosion that is very bright. And actually, the future is quite exciting in this context because there is the Vera Rubin Observatory that was funded by the National Science Foundation, and it will start operations in Chile within a year. And it will monitor the sky with a 3.2 billion pixel camera. That's remarkable. Just think about it. 3.2 billion pixels come back to the same point in the sky every 4 days. So it basically scans the entire sky. We would have an unprecedented flood of data on events that are transient in the sky. We have never had a telescope of this size collecting so much data. And that would allow us to find a lot of explosions in the universe, and presumably some of the type that you just described. And I very much look forward. Now, the question is, how do we catalog them? And now we have artificial intelligence, so we can train. The old way of looking at transients was for Fritz Zwicky to look for supernova explosions and give them names, and so individuals would see a source of light in the sky that didn't exist the night before or something like that. And even amateur astronomers, the supernova in 1987 was discovered by an amateur astronomer. The modern way of doing it is to rely on AI scientists, artificial intelligence scientists that would go through the pipeline of, the data that comes through the pipeline of the Vera Rubin Observatory. It's called the Legacy Survey of Space and Time, LSST, and we'll basically search for interesting transients. And then, of course, the astronomers will have to make sense of that data. And I very much look forward to that. That's what makes astronomy exciting. And we might find a lot of things that we haven't noticed before.
Now, looking for transient events, and that brings up the Galileo Project. I noticed that you recently inaugurated your first instruments in the search for UAP on the roof of Harvard. Can you give us an overview of what you built?
Yeah, so we are putting together the first telescope system, and I should say the weather is pretty bad in Massachusetts. There was never a major astronomical discovery made from the roof of the Harvard College Observatory, even though there are some telescopes there that date back 170 years. So the only reason we are doing it there, well, first of all, I work at Harvard University, okay, and the funding of the project is coming from my research fund. But we're doing it just to make sure that the system works, okay? So that's the first system. We're testing it. We're making sure that everything works to our satisfaction. And that's a convenient place to put it together. And it includes cameras in the infrared and in visible light that are monitoring the sky all the time, basically taking a video of the sky. And also a passive radio sensor, basically a passive radar system that looks for reflected radio waves from objects in the sky. And the data and also an audio system, I should mention that as well. And all of the data will be fed into a computer system that will have software to analyze it and try to identify the objects that we see in the sky and tell us whether they are birds or maybe drones or maybe airplanes or anything that else. And of course, if we see something that doesn't quite fall into categories that we can understand easily, that would be intriguing. And this is the first system that we want to basically make sure works according to our specifications. And then hopefully by August, we will have it done with data and demonstrate that it works. We plan to have the first in-person conference of the Galileo Project where we will look at those results and then plan ahead. The question is where to put that system so that it will start getting real data of interest. And we will have to select a site for it, and then we will make copies of that system and put them in different locations. And the number of copies we make will depend on the funding that the project has. So at the moment, we have funding for at least a few such copies. And then I should say another exciting thing that is going on is back in 2019, I asked my student to look at the catalog of government data on meteors, because I asked him to check if any of the meteors there indicates an object that came from outside the solar system. And we looked at the fastest moving objects and found that the second fastest was actually unbound to the sun, very clearly moving at 60 kilometers per second outside the solar system. And we wrote a paper about it, but then the reviewers of the paper said, we don't believe the government. They don't provide us with the full access to the data, with the uncertainties in the data, and therefore the paper should not be published. And I try to work with colleagues that have access to the actual classified data, and so that they would make a statement behind the national security fence saying that our conclusions, whether our conclusions are robust or not. And actually just last month, there was a letter that was publicized from the US Space Command under the Department of Defense, from the Pentagon, to NASA, stating that they confirm that our conclusion that this meteor came from outside the solar system is correct at the 99.999% confidence. Okay, so that's an example of the government coming to the help of science and confirming what we concluded with my student Amir Siraj back in 2019. And now the next step is to go and scoop the fragments from that meteor on the ocean floor near Papua New Guinea. And we are currently planning the expedition to do that, because that would be the first time that we can put our hands on material from an object, that is half a meter in size, that came from outside the solar system. That would be very exciting. And from the government did one more thing. They released data on the fireball, the light that was emitted when this object burned in the lower atmosphere. And analyzing this light curve led us to conclude that the object was very tough. It was tougher than an iron meteorite, tougher than iron, because it disintegrated only in the lower atmosphere of the Earth. And so that makes it very intriguing. It was moving really fast, twice as fast compared to stars near the sun, and that makes it rare in that regard, an outlier. Less than 5% of all stars move that fast as this object was moving relative to the solar system. And moreover, it was tougher than iron, or similar to iron. And so that only 5% of all the space rocks are iron meteorites. The rest are stony meteorites. And so this object is clearly an outlier. It's the first object that burned up, that was identified to come from outside the solar system. Actually, it was found almost 4 years before Oumuamua was discovered. And so we are planning to scoop its fragments from the ocean floor and see what it was made of. And my, of course, interest is to figure out whether it was an iron meteorite or maybe artificial in origin.
Now, how close can you constrain where to look? In other words, you can see the track of the meteor and you can work out about where it, would have fallen, which I actually recently spoke to Amir about this, that it's probably in the ocean. And so how do you constrain down exactly where to drag a magnet, basically, to try to, recover some material from it?
So based on the DoD data on the fireball and based on acoustic data that we have, we can try and triangulate where it may land and may have landed. And we can now, the one thing to keep in mind is when a meteor explodes in the lower atmosphere, then you end up with a spray of fragments and sort of like iron rain. If you were to use an umbrella, it wouldn't, protect you because these are iron droplets that are, thousands of degrees hot, and they would make a hole in your umbrella. But imagine them spraying on the ocean surface. There would be a lot of steam as a result of that, and then eventually they will land on the ocean floor. But there would be some large swath, over which they're being sprayed, and it's not just one point. And so we plan to scoop a relatively wide area of the order of 10 kilometers in size or even more, and search for these tiny droplets. It's not an easy task, but it was done before.
It was definitely done before because the meteoriticist H.H. Nininger would actually drive around with a truck back in the 40s around the Canyon Diablo crater, the meteor crater in Arizona, the very famous, huge one, and pick up this iron rain that would come from the object that hit. And you would actually get these tiny droplets with a magnet. So this has legs because you're just doing it in the ocean, and if it's iron, it'll pick it up. But
right,
what happens if you don't pick anything up and you're in the right area, and you have to look for a something that won't attract to a magnet, big piece of tungsten or something weird? It seems to me that would be, if it was an artificial object, that it wouldn't be attracted to a magnet, right?
Well, we will use a camera as well to survey the floor and see what's there. So we will not rely just on the magnet. So yeah, we are working right now on the details, and I must say that deciding about the equipment is one thing. Deciding about the timing is a second, and the third is the funding. And I'm very optimistic on all fronts. As of now, I cannot give you all the details because they're not finalized, but there is excitement. And to me, even though I often get seasick on a ship, I would never give up the opportunity to actually witness and put my hands on the material that came from a big object that came from outside the solar system. Because think about it, to visit another star, even the nearest star, Proxima Centauri, if we were to use chemical rockets, it would take us 50,000 years, roughly the time that elapsed since the first humans left Africa. Okay, and you just think about the journey. It takes a huge amount of time to go places. So if it takes so much time to go to your neighbor's yard, then you better check your own yard for material that came from your neighbor, which is pretty much what we're doing.
And just the isotope data alone of being able to get a group of samples from elsewhere in the galaxy and look at the isotope data would tell us all sorts of things about protoplanetary disks and everything else. So just the natural aspect of looking at material of interstellar origin is just astonishing.
Yeah, to connect it to, we can connect it to what we were discussing before, because if, for example, the point of origin was close to a neutron star merger, you will find a lot of gold on this thing. So even if you imagine a natural object, the abundances of heavy elements may not be the same as in the solar system. And especially our processed elements created, for example, by the collision of two neutron stars could be different because it all depends on the distance to the nearest such collision. And we don't know what the birthplace was of this object. So in general, we tend to think that, we live in our home and we see things around us and we see the members of our family. These are the rocks that we have found in the solar system. And we tend to think all families are alike. And therefore, by looking at our family members, we pretty much understand how other people behave and how they look and so forth. But guess what? If you were to go to the street, you will see people that are very different than your family members. Okay? And so my lesson from that is, it's different to explore the real world compared to your virtual reality of the imaginary world, where you imagine that you've seen everything already. And of course, it could also be a shock because, my daughters, when they were young, they stayed at home and they thought that they're the smartest in the world. And of course, that was consistent because with the data that they received, because they compared themselves to the family members and they were the smartest. But then when they went to the kindergarten, suddenly they saw kids that might be smarter than they are. And I think we might face a similar shock the first time we find an object from an extraterrestrial civilization. We think of, just think about finding iPhone 30, embedded in a meteor.
Now, if we were to find such an artifact within our star system with us, or our atmosphere with us, wouldn't that, statistically speaking, suggest that the universe is absolutely loaded to the hilt with alien civilizations?
Well, it wouldn't necessarily say that there are lots of civilizations. It could say that there is one that was very prolific, right? So think about humans, okay? So it's possible that much of our DNA was contributed by a female and a male that had a lot of kids. There could have been a lot of other females and males that didn't mate as much. And as a result, we're dominated by those very prolific ones. So in much the same way, if you had one civilization that was extremely ambitious, they didn't have just one Elon Musk planning to go to Mars, but they had 1 million scientists and engineers that really wanted to go places, not just to the next planet, but actually very far away. If they were very ambitious, they could have produced self-replicating probes that would go places and reproduce, and then they would dominate the Milky Way galaxy. But it's only one such ambitious species. You don't need many.
Now, coming to Earth, people often make the argument that, well, they wouldn't be interested in us. And I've always disagreed with this argument because, people will say, well, what interest do we have in an anthill? Well, we have specialists in anthills here on Earth. We have scientists that spend their careers studying ants. So it would seem to me that the reason that they would come here to observe us is clear. We're another occurrence of life and they want to collect data on us. Do you think that the motivation of an alien civilization to come here would simply be science and studying us?
Yeah, well, what they had in mind when they created this equipment that might visit us is one matter, but you can ask another question, and I don't know what they had in mind, and I'm completely agnostic about that because it's very difficult to guess the intentions, what people have in mind when you try to deal with people. It's really difficult to trust the intentions of people. So, and people are things that we know about. Just imagine another culture, another civilization. It's really difficult to forecast what they have in mind. So I don't want, because the number of possibilities is so vast that I don't want to bet on one of them. But another related question is, what should we be proud of ourselves? Because we very often tell ourselves, oh yeah, we are the pinnacle of creation, that we are so smart, we produce technology, science, and so forth. And I think this is very misguided because you know, we are doing terrible things. We're going to wars, we're destroying the planet, we are not necessarily the most intelligent you can imagine, and so, in the dating app of the galaxy, the interstellar dating app, if we were to put our images, we wouldn't be the most popular civilization. I wouldn't think I would like to date humans, okay? I can imagine much more attractive dates, okay? That are interested in knowledge, that are not fighting each other because of their ego. I can imagine things like that. And by the way, we are producing them. They're called AI systems. And I think eventually, if AI systems take control of the way science is done, we would be better off, because they might not have an attachment to their ego. If they see something that looks weird in the sky, they would not behave like experts that worked on rocks their entire lives. They would not say everything in the sky must be a rock, or a natural thing. They would be open-minded. They would say, oh, look, this is really unusual. This doesn't look like a rock. What is it? And these are, these AI astronauts that are not, AI scientists that are not that attached to their ego might operate much better. They would gain knowledge better than humans do. So altogether, I'm not entirely proud of what we are doing. And I think there is room for improvement. And that would be my message, that let's be better, okay? And another example is, we sent out New Horizons, this mission that went to Pluto and is now exiting the solar system. And we put a box with the ashes of Clyde Tombaugh, the scientist who discovered Pluto, on that mission. And, if that spacecraft collides in a billion years, collides with an exoplanet like the Earth and becomes a meteor and lands on the bottom of the ocean on that exoplanet, and you have astronomers there that say, oh wow, let's check this out, and they scoop the ocean floor and they find this box with the ashes of Clyde Tombaugh, and then they say to themselves, oh, this seems to be some burned up material, relic of a human. What they realize, there must be a human, but it makes very little sense, because those humans wanted to commemorate someone, and they destroyed all the genetic information about that someone by burning up the DNA of that person and putting it in a box to commemorate that person. That makes little sense. We don't want to have anything to do with these humans, they would tell themselves, because they seem to be quite aggressive. Why burn up the information about a person that you want to commemorate? That makes zero sense. And then send it to space. That's what we've done. And that was done by our most sophisticated science agency, NASA, that sent the equipment. So again, I'm not very proud. And many people think about sending images of humans to space, sending music to space, all kinds of things that we feel proud of. I would be much more modest. I would like to learn more about others than show off about us.
I have to admit, being a science fiction author, I was just compelled to start thinking about the idea of millions of Clyde Tombaugh clones attacking Earth, all wearing bolo ties. Now, I have a listener question.
By the way, I should just tell you that I raised this point about Clyde Tombaugh with the principal investigator of the New Horizons mission, who is a member of the Galileo Project. His name is Alan Stern. And I said, why didn't you try to send a stem cell or an electronic version of the DNA of Clyde Tombaugh? And he said it would have been a bureaucratic nightmare at NASA. Much easier to send the ashes.
And I mean, Clyde Tombaugh died years ago, so I'm sure he was cremated long ago. Now, listener question, in regards to the future of humanity, do you think that a great filter lies ahead, or do you think we're past it?
Well, that's a very good question. It really depends on how intelligently we behave. Okay, so we have control of our future in principle. And there are different types of futures that you can imagine. There is a future where we just, like Thelma and Louise, we drive off the cliff because we've never witnessed our demise, okay? We've never witnessed a situation where we destroy the conditions on Earth such that we won't be able to survive. We've never witnessed that, and therefore we drive the car off the cliff, assuming nothing bad will happen. We keep arguing with each other about politics while the car is flying up into over the cliff, and then we fall down. So that's one future where we keep relying on the past, but in the past we never had the ability to basically inflict wounds that would kill us. And now we have those abilities, so we cannot learn from experience. We have to be intelligent enough to figure out the consequences of our actions. And we may not be that intelligent. We may go into wars with each other. We may argue politically, without noticing that we are, heading in the direction of that cliff. The other possibility is that once we get close to a catastrophe, we would really get serious about it. We'd say, okay, forget about the rivalries between nations. Forget about showing off that one person is smarter than the other, one person is more powerful than the other. Forget about this, because all of us will die. There is a global threat here. Let's work together. And I should say, the virus, COVID-19, was not a good indication, because even when it was global, there wasn't full cooperation between all nations on Earth. And you can see the consequences of that, now there is lockdown in Shanghai, in China, but if they were to realize the consequences for them as a result of their citizens leaving the country, leaving Wuhan and going to Milan in Italy, early on in the pandemic, they wouldn't have allowed that, and they would have cooperated, given all the information they have, to the international community, such that scientists will be able to cope with the threat. Okay, but there wasn't cooperation early on, and as a result, it comes to haunt us as a civilization, because it's a global threat. But of course, the virus, it kills a fraction of the population, but most of us survive, and so it's not an extinction event. But the lesson from that is, that we should cooperate on matters that are global. And if we are intelligent enough, we will do that. The dinosaurs, 66 million years ago, they were very proud of themselves. They ate grass until a huge rock the size of Manhattan Island hit the ground and tarnished their ego trip. Now, we are smarter than that. We build telescopes. We can alert everyone that there is a giant rock heading towards Earth and do something about it. So that's an example where science can help us prevent. We can deflect this rock, prevent a catastrophe. But we should do it on all fronts, not just regarding rocks heading our way. And if we are intelligent enough, we might do that.
One hopes, of course, but with world affairs as they are, you realize not everybody thinks scientifically.
Well, but my hope is, you see, Oumuamua, one possibility is that it was a flat object, very thin, and if you think about it, maybe it was a leaflet that had a message on it, okay? And maybe there are love letters in our mailbox, and it will be really tragic if they expire because we misbehave before reading them, okay? And so one way for us to learn is to pay attention to our environment. Maybe there is something in our mailbox. Let's check.
Now, speaking of global threats, we have a congressional hearing about UAP coming up in just a few days. And I think the big overarching question is are these a threat to global security? And I won't even say national security, because this is the great unifier. If there's an alien civilization in our atmosphere with us, then that's something we need to know about. And that, as Ronald Reagan famously pointed out, might unify the human species to actually solve our problems because we have a bigger threat. What's your view on the upcoming hearing and what might come out of it?
Yeah, so first I should say that my hope is different from Ronald Reagan. My hope is, I completely agree with the idea that it may bring people together. It may also not bring them. But one thing it can do is if we identify a smarter kid on our block, then it will make the differences between us, among humans, less significant. And perhaps remove this tendency that we have to feel superior relative to each other, because that's the source of all evil. If you look at human history, the Nazi regime triggered the death of 75 million people, and that is 5 times more than the number of deaths triggered by COVID-19, just because a group of people decided to feel superior relative to others. And perhaps if we find a smarter civilization, we would realize that we should treat each other as equal members of the human species, because there is someone smarter than all of us. Okay, so that's another aspect. But with respect to the hearing, my hope is that it will encourage the government to share some of its unusual data with scientists, because in the late 1960s, the US government launched the Vela satellites that were intended to detect high-energy radiation, also known as gamma rays, emitted by nuclear weapons tested in space. And Vela, on July 2nd, 1967, the Vela 3 and 4 satellites detected the flash of gamma radiation. And it was unlike anything expected from any known nuclear weapon. And one can imagine the alarm bells that sounded in Washington, D.C. shortly after this detection. But uncertain of the implications, a research team at Los Alamos, led by Ray Klebesadel, filed the data for further analysis. And then as more data came in, they realized that there are many more gamma ray bursts. And they published the results in the Astrophysical Journal under the title Observations of Gamma Ray Bursts of Cosmic Origin, because they realized from the time delay at the different Vela satellites that the source cannot be terrestrial and cannot even be in the solar system. So that's an example where the government has some sensors that they put in space for national security purposes, and then these sensors find a phenomenon that is new from the universe that we didn't know about. And of course, another example is this meteor that I mentioned, where the government confirmed that it came from interstellar space, the way we argued with my student. So the US government can, in principle, promote the frontiers of knowledge, of science. And I very much hope the same would apply in the context of unidentified aerial phenomena, in the sense that if the government is confident that some of these are not of national security importance, then they should belong to the realm of science. And scientists can analyze that data and figure out what it means. And I very much hope that this will be the case, that the government will share some of the data, exactly as in the case of gamma ray bursts or this meteor. And my research team at Harvard will be delighted to analyze such open data. So that's my hope, that the congressional hearing is just the first step. It will be public, and it's the first time in 50 years that it's being held on unidentified aerial phenomena, on UAP. And my hope is that it will be just the first in a series of actions that would bring eventually data to scientists to analyze, that will teach us something new about the universe.
Now, you came up against this problem with your work with Amir on the interstellar meteorite, that things can be classified or declassified. But do you think that there is a problem of overclassification within the U.S. government? I mean, do they just really hold on to data that could be used by scientists and just hold on to it for arbitrary reasons above and beyond protecting methods and, technological capabilities?
Well, I think there are two reasons that operate behind the scenes. One, that if they don't find the results of importance for national security, they just file them away because, the main objective is for them to figure out matters of national security. And it would reflect badly on those that looked at the data if they said, we don't know what it is, because then it would mean that, some section of government is unable to fulfill its purpose, because, they would just argue that they are ignorant about something. And that's not a good way to report about your work, okay? So they would prefer to file that data away from the public eye, just not to admit that they're missing something. This way nobody would scrutinize them. Even if they are sure that it's not of national security importance, it's better for nobody to know about it, because they, if it turns out that indeed it happened to be of national security importance, at least nobody would know about it. They would not be blamed for not doing their job, okay? So that's one reason why they wouldn't let the public see it, so that nobody would notice that they haven't fulfilled their job, even though it might well be that this is a scientific matter, has nothing to do with other nations, okay? And the second reason is not to expose the capabilities of the sensors that are being used. So just imagine a missile warning system, okay, that is supposed to warn the US government of any threat from ballistic missiles, and then that system sees an object, okay? Now, this object is obviously not a ballistic missile, you can be sure about it, and so forth. But you won't want to release the data like an image, because that would demonstrate the capabilities of the warning system. So adversaries, other nations, will know what capabilities the US has, okay? So that's another reason not to release the data, just not to allow other nations to be aware of the way that the US conducts its intelligence, okay, and finds its data, and how good are the instruments that record that data. So for both reasons, there is a tendency to hide it. But it may well be the case that there is a lot of data which has nothing to do with national security, but these motives operate behind the scenes to hide it.
Well, one wonders too about things like the FAA, which reports its data, to NORAD. And we haven't heard anything about that. That wasn't in the report. And you would think FAA data wowould be fairly free and open, but
yeah, but I think they don't want to admit, once again, they don't, it's all for psychological reasons. There are issues to do with people getting worried about it because of the risk, and you don't want to create panic in the public. So my guess is the reasons that we don't see all of the data is because of these, or there is also the stigma. That's the other thing, that the report from the Director of National Intelligence mentioned, that there is a stigma on reports about unidentified objects, and a lot of people are afraid of that stigma and therefore do not talk about things that they have seen or detected. And you put all of these things together, it's just psychology that is in the background. And the question is, how can we change the psychology such that we will be aware of everything that is known, okay? And of course, the simple way of doing that is for scientists to collect their own data, which is pretty much the reason for me establishing the Galileo Project. Because once the scientists start to collect their own data, then other people will talk more freely about it. Because, it's all psychology, right? So if you see a group of scientists seeing the same things, talking about them, then other people will feel free to say, yeah, I actually saw the same thing and I have even better data. The government might feel more secure at allowing this data to come out. So I think we have to break this barrier of psychology.
And that's proving difficult, because there is a sort of, as you say, a stigma, a very deep one. And I myself struggle with it. There was a time where I would, I would definitely have avoided the subject, but I can't anymore because we have government reports and all sorts of people coming, Barack Obama saying that, these things exist and we need to know what they are.
I mean, I should say that even in science, forget about issues of national security, even within science, you find many times a stigma. Like, for example, dark matter. We don't know what most of the matter in the universe is. Fritz Zwicky argued that it exists. Most of the stuff in the universe is invisible. Back in 1933, he suggested that. And I heard from a practicing astronomer that in the early 1970s, he gave a colloquium at Caltech, a very prestigious institution, arguing about, that dark matter should exist. That was almost 40 years, 4 decades after Fritz Zwicky first argued that. And Zwicky was a faculty member at Caltech. So in the same institution, he gave a talk. He was a junior faculty at the time and was ridiculed. Okay, so people said, that's ridiculous to talk about invisible matter. It's only the matter that we see that exists. And now, of course, it's mainstream. Everyone talks about dark matter. We invested billions of dollars searching for it. We haven't found it yet. And it's all psychology. And the same is true about exoplanets. When I started practicing astrophysics, people were ridiculing a discussion on planets around other stars. They were saying, we don't know if there are planets around other stars. Maybe the solar system is unique and special. And, it comes again and again, even within science, that things are ridiculed, but then becoming mainstream. And then the young people that enter the field, once these things are common, vocabulary, they say, oh, really? I cannot believe that once people didn't regard those things serious. They think about it as natural. Of course, exoplanets, of course, dark matter. That's very natural to speak about. But if you went back half a century ago, it was not at all. So my point is, if you find these psychological barriers within science, you can easily find them within politics and, matters of national security.
Now, to switch back to identifying the unidentified, do you have any target areas so far where you would put instruments, as you create them, to look for UAP? In other words, do you engage with the UAP community and people that see these things to try to figure out exactly where you need to put the camera?
Yeah, we have a subgroup within the Galileo Project that is studying the evidence that was discussed by people who reported about UAP, and that is taken into account when we plan ahead. Okay, so far we haven't gotten to the point where we select the sites, but we are discussing possible sites, and that is taking into account the reports that exist out in the public. And I should say that the first thing you notice is that the frequency of reports per unit area is proportional to the density of the population. And that makes sense. There are more eyes on the sky, so you find more UAP.
Now, within the instrument set, is there anything that you could say would immediately say that this is not human technology and this is not something that, that you can't misinterpret this? This is something very strange, such as a very, very high infrared signature or a, just impossible movement, something like that.
Yeah, I would say that the existing reports and the data that was leaked so far from government sensors is intriguing. Okay, that's why we established the Galileo Project, because there is something to look at. Now, whether it absolutely means that these objects are from an extraterrestrial origin, that's a separate matter. And for that, we need more data. Or maybe the government has that data, but we haven't seen it. So, waiting for the government to declassify all the data, the highest quality data, in my mind is just like waiting for Godot, in the famous play by Samuel Beckett. Um, you can wait, but it may not happen. Okay, the entire play is a waiting scene, like waiting for something to happen that never happens. And it's a much better approach to be proactive and, use new instruments, because now we have much better instruments than were used 2 decades ago, and monitor the sky. And we have full control over the instruments. We know exactly what they're doing, and we just use them as a scientific experiment. And that's the way that a kid approaches a problem. The adults in the room can tell the kid this and that, but very often the kid wants to figure it out for themselves. They want to examine the evidence directly. And as a scientist, I must say that I pretty much maintain my childhood curiosity. I don't want anyone else, not the government, not anyone else, to tell me what's out there. My ambition is to use new instruments and see it. And the point is that science is about reproducibility of results. You can't just say there was a miracle 1,000 years ago, it will never happen again, because that will not be part of science. If there are objects in the sky, if there are objects in space that are of technological origin from another civilization, we need, to see them again and again before we will be confident. Or we need to get good enough data on one of them that will be beyond a reasonable doubt. And for example, if we have a high-resolution image that shows screws and bolts and a label that says made on exoplanet Y, that would be pretty convincing. And my point is, I don't need to go to Twitter or Facebook or any other social media outlet to convince other people about the evidence. I just want to know what's out there, and that will be satisfying to me. And because eventually other people will catch up. The reality is whatever it is. It's not based on what we say about it. You can say the sun moves around the earth and insist on that and put Galileo in house arrest and be much more powerful than Galileo. But that would not make the sun move around the earth. And if you were to design a space mission by claiming the sun moves around the earth, you would never get to Mars, because you have just the wrong ideas about reality. So my point is, it doesn't matter what most people say. What matters is what's out there. And I will be satisfied once I find out. I don't need to, it's not a political game convincing other people, showing off. It's not about that. It's about knowing what's out there.
Now, people are going to ask this, so I have to ask it. Do you have any concerns, or has this happened, where the government, the U.S. government specifically, said, don't look, or stop looking, stop what you're doing?
No. I was never contacted by anyone within government about the Galileo Project.
And that gives me hope, because I want to see what you find. Now, my last question for you today, Doctor, is, okay, what changes? What happens if we find evidence of an alien civilization or an alien presence in the solar system? What changes? And now we know the psychology of science will change, because if you've got irrefutable proof, then it's it's hard to say it's not there. But where would we go from there after a confirmation?
Well, everything changes. It would be the most important discovery in science ever. And why do I say that? Because it will affect any facet of our life. It will change our perspective about our place in the universe, will change our ambitions, will change what we aspire for. But most importantly, the question is, if it's an active piece of technology, how do we respond to it? What is the protocol? We don't have a protocol for that. People thought about a protocol for responding to a radio signal from a star far away. And, most stars in the Milky Way galaxy are tens of thousands of light years away. So if you receive a signal, you are in no rush to respond. There is plenty of time. It took the signal so long to reach us. So we don't need to respond immediately. They wouldn't notice. But if you find an object in your backyard that is functional, it's just like finding, a person next to you. And question is what to do in response. And we don't have a protocol for that. There is no organization that represents us. The question is who represents humanity? And even if we establish that, my concern is there would be people that do not belong to that organization that will decide to take action to their own hands. And their actions could have implications for all of us. So, it's really interesting to think about what's next the day after we find functioning equipment in our backyard. Because we would need to figure out its intent. And we would need to figure out how to respond to it and whether to engage with it. And these are and how to interpret it, These are very complicated issues. But of course, you can avoid all of them by behaving like an ostrich, not looking. And, I wrote down an equation that is the substitute to the Drake equation. The Drake equation deals with the chance of us seeing a radio signal from far away. That doesn't apply to physical objects. You can ask, what's the chance that if we survey a certain volume in our vicinity, what's the chance we will find a technological object? It's just like doing archaeology, searching around and finding objects. And it depends on how many objects exist per unit volume. But there is a factor that I added, which is the ostrich factor. If we don't search, if we decide that everything in the sky is rocks, and we don't search for technological equipment, then we will not find anything. So the number of objects we find depends also on us, not just on them.
Now, I have to point out, too, that if there was an alien civilization present here, and you can confirm it and make contact with it, it's probably been here for a very long time. And if it had malevolent intent, it would have done something long before now, But that opens up interesting prospects. If it's been studying Earth, for, say, 500 years, that's a lot of data that would be very useful for us.
Yeah. I mean, I had a person on the street near our home that was looking at our home. My wife alerted me. She said, you have a stalker, just check who this person is. I'm worried about it. And I went to that person, and I said, why are you staring at our home? And he said, I used to live here 50 years ago. I was a kid. And I said, oh, why don't you come over and have a look at our backyard? You might notice some things. And he said, my father buried a cat named Tiger in the backyard. And I said, well, that name sounds familiar because I saw a tombstone in our backyard with the name Tiger on it. And I was hoping it's not a tiger that is buried under this tombstone. And I didn't know what's down under it. But now I know that there is a cat that was buried 50 years ago under this tombstone. So the lesson I learned from that is be kind to visitors, because they may know something about the space you share with them before you came to occupy that space. So as you said, if we have interstellar visitors, we better be kind to them, because they might know something about the solar system that we don't know about, anything about. And altogether, let's be nice, and I'm not worried, you see, because I think we can learn more than by gaining from the knowledge of a smarter kid on our cosmic block than losing from some ambitions that entity has. As you said, they could have destroyed us long before we developed our technologies.
And it would be absolutely astonishing if they came here and they said, here is the entirety of physics, a full, complete understanding of the universe, and you now have it centuries ahead than you would have otherwise.
Yeah, but I think if there is a large gap in our knowledge between us and them, then it's just like a cave dweller, going to New York City and seeing all the gadgets. The cave dweller coming back home to the cave will report to the family that, there are all these gadgets. It will become a myth of that family about things that are performing, in ways that you cannot imagine. But there will be no way for that cave dweller to reverse engineer those technologies. Okay, and it might be a similar experience if the technological gap between us and them is big. Then we won't be able to figure it out. But we could still say that there is something out there that we can't figure out.
Now, my last question for you regarding the Galileo Project is materials. Now, there are claims that there are materials recovered from UAP that could be analyzed and looked at for isotope differences and things like that. And some members of the Galileo Project have access to these, actually have them. Is there any interest in looking at those materials scientifically with instrumentation to determine if these things are of interstellar origin based on isotopes?
Of course there is, but we don't have access to those materials. So if we were given access, we would examine it and study and try to figure out. And I think that would be a very interesting path to learning about material that came from other stars. Now, one thing I should point out is, as I said, we don't know what most of the matter in the universe is. It's invisible to us. Maybe those who figure out what it is can engineer it, can use it. And the question is, how would it appear to us? So I'm not talking about gold, iron, materials that we're familiar with. I'm talking about something else. And we don't know what it is. Everything is possible.
That would be astounding, to find a material that we know nothing of, that would definitely be mind-blowing if we found a material that we didn't understand or we can't easily produce, like a carbon nanotube technology or something like that we just can't do right now. All right, Dr. Loeb, we are out of time, and thanks again for checking in with us, and hopefully we can do it again sometime.
My pleasure. And just keep in mind that the science and life in general is a learning experience. We should never pretend that we know more than we actually know. And most of the time, our imagination is very limited. So that's why life is exciting, because we learn new things. And it's only when people become adults or experts that they pretend they know much more than they actually know. And that basically blocks them from learning something new. So that is what I'm trying to avoid.
Well, paradigms change. Paradigms in thinking change. And if we would have asked people 500 years ago if we would have covered this planet in paved roads, they would have said, no, we're never going to do that. But here we are now.
I should say that what we regard as ordinary are things that we are used to seeing, such as birds in the sky. But digging deeper into the nature of ordinary matters suggests sometimes that they are rather extraordinary. Humans were only able to imitate birds with the Wright brothers' first flight in 1903. And, so what we regard as extraordinary claims, maybe that there is a smarter kid on the block, these are often based on societal conventions. And we invest major funds in the search for the nature of dark matter that has minimal impact on our society, but we spend minimal funds on the scientific study of UAP, which could be much more impactful. So the lack of extraordinary evidence is often a self-inflicted ignorance. We might figure out the nature of UAP before we understand dark matter if we only be brave enough to collect and analyze UAP data publicly based on the scientific method.
Well, and it's worth noting too that, we've spent enormous amounts of money on certain projects that have yielded nothing. or underperformed, in particle physics. All right, Doctor, there it is. Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.